This is Knowledge Engineering with Semantic Web Technologies, lecture number 4, OWL, Rules and Reasoning. And today we want to talk about OWL classes, properties and individuals. Okay, so OWL ontologies usually consist of the 3 following building blocks. We know that already. So first of all, we have classes, which are, of course, in the end somehow comparable with the classes we already know in RDFS. Then we have individuals, which are comparable with the class instances in RDFS, and we have properties, or roles, as they are also called in description logics, which are comparable with properties in RDFS. But in particular, they are a little bit different, and we will see this now. So first of all, there exist 2 predefined classes in OWL. And we know that also already from description logic. So first we have a top element and we have a bottom element. And the top element in OWL syntax is called OWL thing. This is the class that contains all possible individuals. And you can, for example, also define this in description logic as the top element is equivalent to the disjunction of any arbitrary class C and its negation. And it's the same with the bottom element, which is called OWL nothing in OWL. This is the empty class, and the empty class is equivalent to an arbitrary class C conjunctively combined with its negation. And if you want to define a class in OWL, it's pretty simple. You simply give the class a name. So here, for example, you define that book is an OWL class. And this, of course, is in Turtle. This A denotes nothing else but RDF type. So this is a further abbreviation possible in the Turtle syntax. So a book is a class. Okay, then if we want to define individuals, which are class members, so you define an individual via class membership. Here, for example, you can say 1984 is a book. So 1984 has RDF type book, and we have already declared or defined book on the previous page. Moreover, in OWL2 you also have the possibility to define an individual without explicit class membership, and this then is a so-called named individual. So individuals can be defined without explicit class membership as so-called named individuals. And here, for example, I could define myself as an OWL named individual. So OWL named individual is nothing else but a special class reserved for the use in OWL for things which up to now do not belong to any other class. So they are named individuals, I can talk about them, I can make assumptions about them, and I can do reasoning also with so-called named individuals. So this is special and this is new for OWL2. Next, let's have a look at the properties. So here, probably the same as in RDFS, here the properties come in 2 different variants. We have on the one hand so-called object properties, for which the object or the range of that property is a class. And we have data type properties, for which the range of the property then is a data type. So simple distinction. And for object properties we can define them with a special syntax part of OWL with the so-called OWL object property class name. And here, for example, we define author to be an object property. So we know now that the classes or the range of that property must be a class. So therefore then we define further on domain and range, and we can here use the RDFS syntax that we already know, and we say, okay, author is applied on the domain book, and every book has a writer. So the domain of author is book, and the range of author then is writer. So therefore this is an object property. The range is a class. What you see here also in gray is the related description logic expression for defining domain and range, and we haven't talked about that up to now. So this is a bit complicated, or it reads a bit complicated if you define that. So it expresses exactly the same, but of course, as you see here, it reads difficult. So if you look at the domain, for example, the domain is here referred to as something which, for which something there exists. So if you use the property author applied on any range, so you don't do a range restriction here, so then this author must have the domain book. This is a subset of book. So this means the first line here. And the second line, again, also looking a little bit awkward because here you have the top element on the left side of a hierarchy, of a class hierarchy, but in the end it's nothing else but an equivalence. But you should think a little bit about it. It says simply that for author, also for the property author, okay, we fix the range writer and we fix this for all possible applications. So author cannot have any other range, no matter whether we here talk about author or anything else. So therefore here what we talk about on both sides of this equation is the top element, but we fix to author, to the property author, the range writer. So this is pretty simple, but you have to think a little bit around the corner for that. Okay, so this is domain range for object properties. Let's have a look at data type properties. Of course, there is then also a vocabulary expression for data type properties. Here, for example, I define the publication year as being an OWL data type property. And then, of course, I have to define domain and range. And again, this publication year, I apply it on book. So the domain is book. And then the range will be a data type. And I can here take data types again from a subset from all available XML schema definition data types. So here, for example, I can use an XSD integer. I could also use another kind of number expression that is available in that vocabulary as a data type. So this would be a data type property. So we have object properties and data type properties. If we take everything together, we have here a nice example. So for example, we define simply book is a class, writer is a class, and then I define author as being an object property which has the domain book and the range writer. And then I define publication year, a data type property which has the domain book and is applied on the range integer. Next, I define individual. So for example, George Orwell is a writer and 1984 is a book. And 1984 has the author, George Orwell, and it has the publication year 1948. So you see, this is quite simple, and it's also pretty fast and pretty easily written in Turtle. So this is an example for OWL, classes, properties, and individuals. In general, these property definitions are not functional. What does that mean? So let's have a look at this simple example. I define here a genre, and I say genre is a class. And then I define 3 different genres, which are instances or individuals, which are members of that class genre. First is political fiction is a genre. Then I say science fiction is also a genre. And dystopian fiction should also be a genre. So then I define an object property which I call literary genre. And this should be applied on the domain book and should have the range genre. So next I can say to which genre the book 1984 belongs. And I say 1984 is a book and it belongs to the following literary genres. It belongs to political fiction, science fiction, and dystopian fiction. So this is not restricted to a single use. This means this is not functional or not necessary functional, simply because I did not declare that object property to be explicitly functional. So therefore, in general, it's not functional. Here you see it in a simple example. Okay, what else can I do? Of course, I can define class hierarchies. So here, for example, I have a novel, which is an OWL class, and the novel should be a subclass of book. So the subclass relationships I express with the already existing RDFS vocabulary. So I can say novel is an RDFS subclass of book, and then I can say, of course, book is a class, but this is also implicitly given by the subclass relation I have here. And then I say book is a subclass of work. And work, of course, is also a class. The interesting thing here, and we also could do this with RDFS via inference, it could be entailed that novel then must also be a subclass of work. So this subclass relationship, again, like in RDFS, is transitive. So these are our class hierarchies. Then, of course, I have the possibility also to define restrictions on these classes and class hierarchies. So restrictions, for example, like disjunctiveness of classes. So look at the following example. I define here some classes in the class hierarchy. So first I say book is a class, writer is a class. And then I say novel is a subclass of book and poet is a subclass of writer. Then a new thing, I define that book should be disjoint with writer. So book and writer are two disjoint classes. The interesting thing now is that via inference, it can be entailed that also the subclasses of these major classes which have been defined to be disjoint, they must also be disjoint. This means that novel and poet are likewise disjoint then. So here I can define disjointness of classes. So this is pretty interesting for two classes. So now just imagine I would have 4, 5, 6, 10 or even 100 classes. The problem is then if I want to define disjointness between all of these classes, of course the number of disjoint definitions would increase over proportionally. So simply for that reason, there is a shortcut available in OWL to define several classes to be disjunctive. And this you do in the following way. You define here, or you have in the OWL vocabulary, the keyword OWL all disjoint classes, which itself is a class definition. And here you define here an empty node and say, okay, this empty node, all which is in this empty node is an all disjoint class definition. And then you say, okay, this has the following members. You have here the new OWL property, it's OWL members. And then you have here, behind the OWL members, you define simply, or you enumerate all classes which should be disjoint, and you give this definition in usual braces, and you say then books, writers, vegetable, furniture, and car, these are all classes which are disjoint among each other. So this is a shortcut. You could also write that book is disjoint with writer, book is disjoint with vegetable, book is disjoint with furniture, book is disjoint with car, and so on and so on and so on. But this, of course, is a much faster way to do that. Okay, disjointness. The next thing what you can do, for example, you can also say two classes are equivalent. You remember open world assumption and no unique name assumption. If something is really equivalent or not equivalent, you must have a means to say so. And for example, here, look at the following example. We say writer is a class, author is a class, and poet should be a subclass of writer. And then we can, for example, say, okay, but writer and author, they are the same. So therefore, writer is an equivalent class of author. And from our example here, what can you deduce? Yeah, via inference, it can be entailed that also poet, which is a subclass of writer, must be a subclass of author. So this is pretty obvious and pretty simple. Okay, the same holds for individuals. So you also have to have the possibility to declare that two individuals are the same or are different. Following example, we have here 1984 is a novel by George Orwell as author and with the publication year 1948. And we say this is the same as another ID which we define here, which is ARX 012345. And we say these two individuals, this ARX individual and 1984, they are the same. So then we say novel is a class and novel is a subclass of book, and book is also a class. The interesting thing, simply via these equivalence or same as relation that we defined between 1984 and this ARX identifier, we can also deduce that ARX 012345 is a book in the same way as 1984. And in the same way as you define equivalence of two individuals or identity of two individuals, you can also define difference of two individuals, and you do this simply with the keyword OWL different from, and then, for example, you can say, if you say ARX 012345 is a novel, you can say this is different from ARX 012346, for example. So with OWL same as and OWL different from, you have the possibility to explicitly define the identity or the difference of two individuals. Okay, now, of course, if you, in the course of the definition of an ontology, define many, many individuals and you all want to define them all to be different, you would run in the same problem like in the disjunctiveness problem with the classes. So therefore, also for the individuals, OWL provides a shortcut. And this, of course, is the OWL all different. And here in the OWL all different, you define it in the same way like you did this with the disjunctiveness. So you say a blank node is of type OWL all different, and you say this has distinct members, so all these members are distinct, and then in braces you enumerate all the members that are really distinct or different from each other. And this here are books, for example, like 1984, Animal Farm, Brave New World, and Simulacron 5. So this is a shortcut for declaring the distinctiveness of single individuals. So we had now some basic definitions already introduced for OWL. In the next part of the lecture, we will see how we apply this together with constructors and constraints to define more complex classes.